In this lecture, we're going to discuss a litany of topics, some of which are somewhat related, others are more so standalone concepts. The motivation for this lecture is to be able to ensure that you, the viewer, are able to continue to build a strong foundation as it pertains to the fundamental concepts of the field of statistics. And from such, I aim to assist you in achieving subject mastery. So we'll begin by discussing probabilistic events. We have independent events and dependent events. Independent events are not affected by previous events, while dependent events are affected by previous events. So a good example of an independent event is throwing dice. Every time you throw dice, assuming that they're fair dice, and assuming that they travel a certain distance, etc., assuming there's nothing, no outside factors which are playing on the outcome, we would assume that each roll of the dice is going to present a value which is in no way going to impact the value which is received from a subsequent throw. So if you throw the dice 3 times, and each time you receive 2, 1 and 1 on each head, that wouldn't indicate then that the next roll, whatever value you receive, has any greater probability or reduced probability of occurring. Now, as it relates to dependent events, in this case, an event that happens in the present depends on some way or another on an event which happened before. An easy way to remember this particular concept, or at least envision it, is either bingo or playing cards. So if we have a deck of 52 cards and we're looking to draw a jack, and we draw 4 cards from the deck, none of which are jacks, well, now we have 48 cards remaining in the deck and 4 jacks. So there's a greater probability of receiving a jack on a subsequent draw than there was initially. Because initially, if there's 4 jacks in the deck, it's 4 in 52 probability of drawing a jack. But now that 4 cards have been removed, it's 4 in 48. And if you've ever played bingo, let's say we're trying to have the ball come out of the roller, which is value B1. I don't know how many balls are in bingo, but with each ball that comes out that is not B1, there's a greater probability of B1 coming out because there's a smaller and smaller sample from which our values are being derived. Okay? Relative risk, abbreviated as RR and also known as risk ratio, is the ratio of the probability of an outcome in an exposed group to the probability of an outcome in an unexposed group. So in this case, we have to build a contingency table. And there's a binary variable on the top, positive, negative, exposed, unexposed, and a binary variable on the left. Again, we have a positive and negative outcome. So yes, no. So, affirmative, otherwise, affirmative, otherwise. And what you need to do then, if you want to derive these values, whether it be the overall rate exposed, outcome rate not exposed, relative risk, is you have to structure these equations with the values contained therein, and then that will then provide you with the definitions on the left. So again, you want to have, it might not be exposed, unexposed, or outcome yes, no. You want to make sure that you have the positive and the negative, if it's a binary outcome, and the positive and the negative binary outcomes structured in this manner, and then just follow these various equations, and you'll derive these particular values. So here's an example which was taken from the Wikipedia article on the subject. So if you wanted to do more research on your own independently, go ahead and take a look at that article. But here we have a group that received treatment and a group that did not receive treatment for some sort of, it looks like for some sort of exposure outcome. In any event, everyone on the left who has a pill, these images of these generic images of men here, or they could be women, they received treatment, hence the pill. These individuals on the right didn't receive any sort of treatment. Now, as you can see, as it relates to adverse outcomes, these individuals on the right, regardless as to not having received the treatment, still had an adverse outcome. And these individuals, regardless as to receiving the treatment, also had adverse outcomes. These individuals on the right who didn't receive the treatment had no adverse outcomes. These individuals who received the treatment had no adverse outcomes. So I suppose then a way to envision this is maybe all of these individuals, based on some sort of demographic information that was collected, maybe they're at risk for, I don't know, heart disease or some sort of condition similar to that. And to try to mitigate that outcome, some sort of drug has been derived. And this group over here received it, this group over here didn't. And as you can see, some individuals didn't develop the condition regardless. They didn't develop heart disease regardless as to not, regardless as to not receiving the treatment. So maybe it was just luck of the draw. These individuals, even though they were at a, they had the demographics in which that they may be susceptible to such, maybe the pill assisted in preventing that outcome. These individuals didn't receive any treatment. They still had the adverse outcome. These individuals received the treatment, still had the adverse outcome. So what is the relative risk of such a scenario? Well, this is how you would calculate that particular value. And this is the values as they are drawn from the contingency table. And you would just use the template here. In this particular slide, this is exactly how our data was structured and how it was drawn. Then the question comes, well, then how do we interpret this? This is from the Mayo Foundation for Medical Education and Research. And they provided this chart here, which might be helpful in interpreting relative risk. Ours was 0.5. So 50% decrease in risk, or half the risk. So we could state, and we'd have to put our data or our outcome data below in this format. And then with that, we could then draw our conclusions appropriately. A similar concept is absolute risk reduction, or ARR. And this refers to the actual difference in risk between treated and control group. So this is a similar scenario as it pertains to these individuals who perhaps have some propensity due to demographics for a heart condition. And one group receives a preventative treatment, the other does not. And as you can see, some individuals, regardless as to having received the treatment, developed that adverse outcome, and others did not. So if we wanted to calculate these outcomes, the equations are beneath the contingency table. We have the experimental event rate, or EER, the control event rate, CER, and absolute risk reduction, which is ARR. And how to calculate those, the equations related to such are on the right, and the definition of the value, which is determined from such is on the left. And if we were going to calculate this from this particular example data set, this is what those values would be. Now, speaking more on probabilistic events and outcomes, let's discuss sample space. So sample space in probability theory is also known as sample description space, possibility space, outcome space, which you'll typically hear it referred to as sample space. And the sample space of an experiment or random trial is the set of all possible outcomes of a result of an experiment. So there's some confusion as it relates to this particular topic, but I hope to make that clear. What sample space is looking to illustrate is the possible outcomes for a possible event. So if we have a fair coin and we flip it one time, we would only expect to receive either a heads or a tails. So one fair coin flipped once is either going to yield a heads or a tails. And you would write each particular outcome in these braces here, and then separate them by a comma. A fair coin flipped 5 times, counting only tails. So if we flip a fair coin 5 times and we are only counting the tails, well, we might receive 0 tails, we might receive 1 tail, we might receive 2 tails, we might receive 3, 4, or 5. Again, we're either going to receive, if we're just counting the outcomes. So how many tails might we receive if we flip a coin 5 times? We might get any number of tails from 0 to 5. And maybe don't think of it as one coin. Maybe you have 5 coins. They're all similar, and you're just flipping them all at once. Like you're just throwing 5 quarters up into the air, and when they land, you're counting the tails from the floor. Well, you might have 2 tails, 3, 4, 5. There might be 0. It might just all be heads. A 3-sided die, well, there's only 3 sides to it, 1, 2, or 3. So if you throw that die or cast that die, you would expect to have a face of 1, 2, or 3 shown to you subsequent to the dice being rolled. 6-sided die, you're going to expect, based on the faces, if you're rolling this die once, you're either going to receive a 1, a 2, a 3, a 4, a 5, or a 6. And if we're flipping 2 fair coins once, so again, 2 quarters, we're throwing them into the air, well, what will our outcomes be? Well, we're either going to receive 2 heads, a head and a tail and a head, or a tail and a tail. Okay? Test sensitivity is also known as the true positive rate. It's the probability of a positive test result conditioned on the individual truly being positive. Specificity is the true negative rate, and it's the probability of a negative test result conditioned on the individual truly being negative. Whereas a false positive is an error in binary classification in which a test result incorrectly indicates the presence of a condition, such a disease where the disease is not present. While a false negative is the opposite error, where the test incorrectly indicates the absence of a condition when it is actually present. So false positive and false negative. Here is another chart taken from the Wikipedia article related to such. And this presents you with the definition of each one of these terms. And we'll perhaps get into type 1 and type 2 error in a later lecture. Again, we're going to be working with a contingency table. So if you have or require a greater understanding of this concept within the playlist Introduction to Statistics, video 6 is all about contingency tables. So go ahead and take a look at that on this channel if you need some help with these tables and what they're seeking to display and indicate. But if we're looking to derive any of these values, whether they be the PPV, the NPV, the false positive probability, these are the definition of each, and this is how we would calculate them. And you'd have to make sure that the values are appropriately placed in the contingency table, where the positives are in the upper left-hand cell and the negatives are in the lower right-hand cell. And here we have a matter of testing individuals who are either going to be tested correctly positive or correctly negative. So they may have the condition and they may test positive for the condition, or they may have the condition and not test positive for the condition. They may not have the condition and test positive, and they may not have the condition and test negative. Here's how we would derive the false positive probability, the specificity, and the sensitivity from this particular contingency data. So I know we went over a kind of a wide variety of topics in this particular lecture, and we went over them briefly. I just wanted to, again, introduce you to these concepts in hopes that you'll have just such a broad understanding or broad exposure that when we start to get into application and methodology, you won't feel in any way out of sorts. If you made it this far, I appreciate you stopping by. Please like and subscribe if you could. It would mean a lot. And I hope to see you in the next lecture. Take care.